Yeah. So we'll just first go through the content, and then like I'll just try to run the small poll. Just want to know like interest. It will just take like 2 to 3 minutes, and then we like look into the topics. So I'll just showcase the agenda. So about this today's agenda, that like we'll start with like some introduction to like BMS. Okay, like about the measurement and the NXP based BMS breakboard. Like we have been using the NXP as a platform for our like BMS development, as it is one of the industry standard, and also it has a lot of support in terms of like uh, the base software development. Okay, and we have like prepared our own like board, like which works like as a BMS. It is a learning platform board. I'll just showcase that one. And then we'll try to understand the NXP BMS integration to the battery pack. So what all components like we have in a setup, okay? Like in order to work on the BMS thing, like that we can see. And then like model implementation and monitoring the data. So like once you like develop a MATLAB based Simulink based model, okay, so there like you have built up your algorithms and like the logics related like for cutoffs or like for the monitoring thing, and then you need to like whatever the model thing, right, you need to like dump into the that particular logic to the controller. So how it can be done on the NXP board, that we can like look into it. Okay. Yeah. So some like demonstration points like faults management, we can see the estimations, algorithm implementation, and like even the monitoring of the data, such as like all the cell voltages. Okay. Uh, for example, in my case, like with here in the setup, I have a battery pack which is of like 14 cells in series and 3 cells in parallel. So I will be using that battery pack for my demonstration. Okay. Yeah. So what all the data you can monitor, like cell voltages, pack voltage, the current value, like one or temperature sensor, and even the basic SOC estimation, the Coulomb counting based. Okay. Yeah. And we'll try to understand some code generation and its basic approach, uh, and the functionality testing for like, we'll try to do some like charging and discharging that we can like showcase on it. Okay. Yeah. With this, like overall agenda, like we can move ahead. So before that, like I'll just try to run a small poll. Okay. So you can just take your like 3 to 4 minutes and you can just answer. It's a basic one. We will also have the multiple choices for it. Yeah. So once you're done with your poll, you can just let me know. Yeah. I hope you got the screen at your system, like the pop-off of the polls. So yeah. Okay. Just you can like try to answer them. Okay. And then like, yeah, just take your like 2 3 minutes. Yes. It is just kind of some survey thing. Yes. Like I'll just wait for 1 more minute and I will just start into the next part. I just found to know that like 10 more participants have newly joined. Like, yeah, I hope at your screen you have like popped up with some poll. You can just try to answer. Like just take your like some seconds and you can like, yeah. Thank you for like filling up the kind of poll. Okay, poll questions. So yeah, now like I'll just go to into the like inside of these content. Okay. So first, like I will give you a small like introduction on the hardware side, and then like we will go into the setup side. Okay. Yeah. So when we talk about like BMS, right? So we do measure some parameters such as from the battery, that is like cell voltage. Voltage has a parameter, current, which is like as a charging or the discharging, and the temperature. Okay, with these three parameters, like they will like come up with the algorithm development such as like SOC, SOH, and even the functionalities like over voltage cutoff, under voltage cutoff, over temperature cutoff, etc. So how these can be measured? Okay, right? So I'll just go to that particular page. So one thing, like when we talk about like voltage measurement, if you take a single cell, okay, like we know that for a single cell it has like plus and minus. So if you take a controller, okay, microcontroller, so like you will be having like a set of analog pins and digital pins. Okay, so one like the positive of the pin like connected to the analog and the negative to the ground. Okay, then you can able to like measure the voltage. So you will be like sticking with the ADC approach itself. Okay, yeah. So this is like when it comes to a single cell measurement, this is a feasible one. When it comes to the pack level, like let's say like you have multiple cells, like 15 cells, sorry, 14 cells or like 15 cells, 16 cells in a series. So, and you take up a controller and you have limitations in analog pins and in terms of ground pin also, right? So then they came up with the approach called as differential method. So as per I, like in with my experience, like uh, most of the BMSs like following the same approach, the differential method. Okay, so I'll just use some small like idea. So here, like if you take this 4 cell series of a battery pack, okay, so the ground of the battery pack, like the negative of the battery pack will be connected to the ground, and you can see this is cell 1. So the cell 1 positive one will be like going to measure. Okay, if you measure, assuming that you will read 4 voltage, and on the other, you will be taking it for op amp or for the comparison. So, and you connected the positive of the cell 1 to the negative of cell 2, and the positive of the cell 2 again it is going to the op amp here. Okay, so if you read here, like you will read 8, but if you are using the like op amp and like you are subtracting the previous one, you are going to come up with a value of like voltage 4. Okay, so it is just like as simple as it is. So like advantage, if you want to talk that when you are reading the voltage of the cell, there will be a error. So like at each signal line. Okay, so with these approach, you can eliminate that thing, the error. Okay, that is one of the technical advantage I can say right now, and it will also reduce the number of wires and the size of your chip. Yeah. So with this approach, they have came up, and for this, they have went for development of AFE. Okay, so I'll just show you the AFE thing. So this is like AFE board. So whatever you are seeing here, I'll just mark it over here. This one is a AFE development board. So like at the end, you will be making use of only this chip, but this is a development board. So whatever the chip you are seeing, you can just take a note of this number. You can also like search in a well, you'll get more information on this part. So the same NXP, like it has been like placed over here, and these are some AFEs of the different like platforms for analog devices, Texas, NXP, and yeah, etc. So what all functionality like you can find within NXP, that the which one the one which I was showing, that the voltage measurement approach, that is like the differential method. So that will be incorporated within this chip, and also like you can go for measurement of uh, uh, the current, temperature. Okay, yeah. So I'll just cancel this one. Here, whatever you are able to see here, like I'll just show you, like, and even the balancing thing also will be placed over here. Okay, the balancing circuit. So here you can also like connect your like all the cells. So I'll just showcase you. Okay, uh, yeah, just give me a second. Okay. Yeah, just give me a second. I will just share like the video over here. You can just, I'll just showcase it. Yeah. So I hope this AFE is like visible, right? So I'll just place it over here. So this one, which I was like showing in uh, the PPT. Okay. Yeah. So here you can see that MC3 like chip. Okay. And it will be like connecting it to the controller for communicating. And this is where you can like connect all your signal pins of your battery pack. Okay. Yeah. And then this will be your like resist. This will be like your balancing circuit. Okay. So where you can see this particular area. Yeah. And then like balancing resistors, where you can see at the bottom. And this will be like we will be using the NXP as a controller, and then it will just go on sit over here. Okay. So but we have built something called a different platform to showcase like and to control the whole battery pack. Okay. Yeah. So with this, like I'll just showcase you like all the components right now. So this one is the battery pack, where you can see. Okay, I'll just turn off this one. Now we can see. So this one is the battery pack. Here you can see like 51.8 and like 15 Ah. Okay, so all these signal pins. Like when I say 14S, like 14 cells will be in the series. So all these like 14 cell signal pins, like I will be connecting it to my BMS board. So here like I have connected with some like connector called like DB25 stuff, and then like I will be like reading all these cell voltages to the controller, that is a BMS controller, that is we call it as a AFE. Okay. Then it has also have a like something called, you can measure the current through a shunt resistor. Okay. So right now we have been using the external current sensor. We call it as like Honeywell. Okay, it is a CAN based current sensor. So it has something like 4 outputs, like 2 will be like positive and negative, which will be supplied with 12 volt supply with the 2 amps, and then one will be like CAN high and low. Okay, so this will be connecting it to the hardware. The wire which you are seeing with the yellow color and green color. Okay, yeah. And if you see on the battery pack, there is a thick red and black wire. We can call it as like power wire. So that power wire will be, it is passing through. Okay, it is passing through a current sensor. The negative of the battery pack is passing through current sensor, means we are measuring the current at the low side of the battery pack. Okay, and then we are also controlling the battery pack at the low side itself. Then it comes, then we comes here the contactor. So this contactor, we use it for discharging and charging cutoff. So again, this will be controlled by the BMS, the whole BMS board itself. So like we have been using the external MOSFET. So here it will be getting the signal from these 3 pins. It will be getting the signals from the controller, from this controller. Okay, so through the board, it will be coming and it will give the signal, and then the MOSFET will take care of controlling this one, the whole relating the contactor. So yeah, so when it has to undergo like the trip condition. Okay, so once the faults management is triggered, then this will undergo the trip condition. Yeah, and then we are connected to the load. So yeah, so this is a programmable load. Like I'm just like we are using this one, so that we can set up the whole thing, and then we can discharge it. Yeah. So here basically we can see the components like one with the battery pack and the BMS, which is having of AFE thing, and the controller and the current sensor. Okay, and like the contactor part. Okay, yeah. So this is some introduction part. So here, like just turn on this one. So I hope you have heard some kind of noise. That is a particular that noise is of contactor itself. Okay. Yeah. So like right now, like I already dumped the code. Okay. So because of that, like you can see like all the BMS, like you can see some LEDs, like it is turned on. Yeah. So even I will demonstrate like the monitoring of all the voltages like after some minutes. Okay. So yeah. So now you can see at the 10 mass screen, like at this particular screen. So it is reading like 51 volt. So right now the battery pack is of 51 volt. Okay, like it is in a nominal voltage condition. Yeah. So what I'm going to do, I'll just switch back to my screen, and I'll just set up some monitoring thing. Okay, and then you can see like all the individual cell voltages and like about the code generation part, how we can implement, and all the implementation. Okay. Yeah. Just give me some minutes. So yeah, I hope that like video, like the live video was visible. Just let me know in the chat box. Okay. Okay. Yes. So it was just a basic demonstration. Okay. Like we just to showcase like what all the components we have. So I'll just showcase that one also. So the same setup, like what you are seeing over here, the same thing. Like I took a pic and placed over here. Yeah. So now, like we can just go into connecting that particular uh, BMS to a system just to monitor of all the cell voltages, all the stuff. Yeah. So what I'm going to do, I'll just shift back over here. So right now, like this is one of the like free master application where you can like monitor like all the readings. It might be this is for the BMS. Like if you are working on some different like topics such as like motor controller or some other else, you can make use of this application. But it is useful when you are using the NXP boards. Okay. Yeah. So right now, like I hope this screen is visible and you can see the like the cell voltages. I'll just try to enlarge. I'll just check whether it can be enlarged or not. Okay, just let me know. Like, is it visible? This variable watch. So let me show you this one. Okay. So the first one you can see that pack voltage. Okay. Sorry. Just give me a second. Okay. I I think I just moved it. Just yeah. So the first one which you can see is the pack voltage. Okay. And then like all the cell voltages. So if you count it from the zero, it will be like 14. Okay. So including this zero as an index. So all the cell integer voltages and the current. So this one is the internal temperature, which will be reading of the ICs. So just try to enlarge this one. Yes. Yeah. And then uh, the SOC, like we have been using like OCV and Coulomb counting based SOC estimation. So right now, like it is showing like 58 point and the cell instant capacity is 0. Like just now we turned on, right? So like it is showing like 0. Okay. It is just a accumulation of capacity. So yeah, whenever I discharge a charge, it will go on accumulating it. Yeah. So now I'll just come back to here. So if you see here, so like as I was showcasing the load, the 10 mile load thing, right? With this, I will just try to discharge it. Okay. And then you can see a drop of your like readings, all the stuff. So like where you can also like try to see the Coulomb counting stuff, which is decreasing. Okay. So just come over here. You can just make an observation of it. So I just applied 5 amps. Okay. So you can see So you can see like the 5 amps like has been applied. Just let me know like if you are able to see like current value like has been reading like 5 over here, and along with you can see like the Coulomb counting stuff, the SOC estimation, and the instant cell capacity accumulation. So and you can see the drop in the voltages, right? Yeah. So how like yeah, right now like you are just connecting and you are just observing. So how to like see like from where I'm like bringing this connection, right? So I'll just showcase, I'll just come back to that point. So I'll just turn off this load. Yeah. Right now with me, I have this model. Okay. So here, like we have developed like all the balancing algorithm, like faults management, like SOC Coulomb counting and EKF based, UKF based, and like Kalman filter as a general based SOC estimation, and then like uh, false indication and like trip off sequence. Okay. Yeah. So the thing which you are seeing over here. So these are some the pre developed S function modules from the NXP. So we will be using these as a like base software, okay, to communicate with the hardware. So that the application engineer can only concentrate on the algorithm. So right now, like this part is completely application. The logic, the algorithm, the SOC estimation, that all the maths, right? It will be like placed over here. So the one which I'm marking in other color, let's say like blue. So this one and these like all these are like uh, base software, like library block you can say. Okay. So with these, we will try to communicate with the hardware, which I was showing that NXP based like controller and the AFE. Okay. Yeah. So here, like already I have made some settings for the code generation. Okay. So we need to make some changes like with respect to the hardware just to communicate. Okay. Like let's say like target connection and yeah, and these. So and finally, if I go for build, the whole code will be dumped. So there are different methods like to develop the code. I'll just come back to that point. Okay. Yeah. So we'll just go. Yeah. So when we talk about like code generation, right? There are like some approaches we can follow. Uh, if you are like have a hardware like the base software support from your hardware developers, then you can directly go for uh, the algorithm executable approach. So you will be having all the library blocks. You can just like all these uh, the respective like COM drives, device drivers, input drivers. So these supports in terms of communicating to the hardware, right? So you'll just like bring these blocks and try to arrange as per the requirements, and then like connect it to your like application model, and you go for dumping the program into the hardware. So this we call it as like algorithm executable, and the one we call it as like algorithm export is right. So if the hardware platform doesn't have this software support, or like the base software, you can just generate the code only for application model. Okay, you just generate the code for only application model, and later you can like at your respective IDE, you can just communicate the generated code to that IDE, which is having the base software. Okay, yeah. So this is something I can call. So yeah, so I'll just like try to showcase one code generation approach here, like where we can directly dump. So small settings has to be done. Just give me a second. Yeah, this is one of the input SLDD file. So yeah, I need to like make use of this SLD to communicate throughout the board. Okay. So now like I have connected my board, like the hardware to my system. So I'll just go on dumping the program. So I'll just say build. Yeah, I think it will take some few like seconds or 2 minutes. So meanwhile, you can see. So once it comes to the complete download of code to the hardware, all these values will be disappeared and they will reappear again. So let me check. Yeah, it will take some few minutes to seconds. Sorry, seconds to minutes. Yeah. So let me cancel this one. Okay. So let me check once again. Yeah, it is still like taking some time. Yeah. So we'll just wait for like 1 more minute and we'll see the output. Yeah. So there is something that you can also like say that when we try to generate the code, some set of files will be like also generated. We call it as like .elf .mod file. So we can also make use of the .mod files to store the previous generated code. So I hope you have heard that some tick sound. Uh, like yeah. So here you can see the generated code, and if I go back, so it has been asking that ELF and the map file has changed. Would you like to reload it? Yes. So and if I say continue, and you can see, yeah. So this is like something we have been following. Like let me go back. Just a second. Sorry. Yeah. So yeah, I hope you can see just generated code. Okay, lot of settings has to be done. Okay, like when you are going for the build option, generate code and build the model. So like in the background, like we have been worked on, and like we have set up some options like during the settings, like where you can, let's say, like the model settings. So when you talk about like code generation, like lot of settings will be there for the optimization for the reports, comments, and code style custom and verification templates and data type replacement. So this is like some basic options which we need to like look for it. Like if you are a beginner and if you are like the code generating, which is not for like production thing, so you can just like follow the quick start guide. Okay, so with this quick start guide, like you will be having like a set of options where you can follow, and you just need to go on clicking the next and next. So it will make the respective changes for your code generation. Yeah. So just give the overview. The block which I'm like trying to like let me, yeah, this one, right? So I have given a name of MC3371B, which is of AFE. Okay. So with the AFE, like which what all the things I mentioned, like one with respect to the reading the like parameters such as like voltage, current, stuff. So all uh, the thing which you are able to like blocks which are to communicate with the hardware. Uh, okay, this one is not visible. Just let me know. Yeah. So inside this, like we have the AFE inputs. We have like a block where we can get all the data, like cell voltages. Just showcase you cell voltages, stack voltage, temperatures, internal temperatures, and like current, all the stuff. So you will be like once you get the data at your required units, then you can use it for your algorithm development. So this is one of the block which made by the NXP, kind of like you can say as a base model library. So and then whatever the data you are reading over here, okay, at over here, and you will be sending it to respective blocks. Okay, yeah, and then there are some false conditions where we can encounter. For example, like we have the model which is built of like voltage faults, current faults, and temperature faults. So when there is a over voltage, under voltage conditions, so you will get a let's say like a signal, like once you have over voltage, under voltage condition, and this will be uh, like let's say like it will just give the boolean outputs either 1 or 0. So based on that, we will send this data to this particular block, okay, which is able to connect with the PTC16. PTC16 is a pin number at the controller. I'll just showcase you. Yeah, just wait a second. So this one. So if you see over here, there will be some pin numbers over here, right? So like it is one of the pin number. So this pin number will be connected to the controller, like not controller, the contactor, which you are able to see over here. Okay. Yeah. With this, you can like stop your charging or discharging. Yeah. So this is some basic overview, like of the hardware part. Okay. So this is the basic layout which I was trying to showcase. So I'll just try to like explain this part. Like yes. So sorry. Yeah. So the same thing like the battery, the positive. Okay. So right now this SSR you can take it as like contactor. Okay. So you have been like placed a current sensor over here at the negative end and to control over here also. Okay. And this is your like BMS board, and like the positive of the BMS board and the negative of the BMS board. And you will be reading all the pack voltage to like cell level voltages from the battery pack to the BMS. Okay. And then there is some MOSFET module like where we can control the charging and discharging. So this will be the load setup for the charging or to discharge the battery pack. So it is a similar one. Like